we're going to be talking a little bit about limiting reactants. Now this is a word that you're going to be using you've probably seen in the PhET simulation. You're going to be using a little more later on. So to talk about what limiting reactants means is we're going to start by using this prom school dance example. So you're at a school dance, the music starts playing, and everyone starts to couple up and dance together. However, you'll notice right now that there are fewer girls than there are guys, and so we've got two guys that are left out over here. So in this case, what does this have to do with chemistry is what you're probably asking. In this case, we're going to take a look at what the limiting reactant is of this. So you can see that the boys here are the excess material in the dance. So that makes the girls the limiting reactant. So as you can see, the amount of product depends on the limiting reactant. Let's not look at this right now. This depends on the limiting reactant. So as you can see, the number of couples on the dance floor is entirely dependent on how many girls there are, because there are fewer girls than there are guys. So let's flip this over and take a look at a chemistry-related example of this. So we've got 6 sodium, 2 iron oxides, 3 sodium, and that mixes together to produce 3 sodium oxides and 2 iron molecules. So let's figure out what the limiting reactant may be. And you're probably thinking, well, that must mean that it's the smaller number. That's kind of a common misconception. The smaller number is not necessarily the limiting reactant. It's how much of the smaller number you have. So if you have 1 mole of iron oxide, this is what this is saying, then you would need 6 moles of sodium. So it's all about the ratio. We've got 6-to-1 ratio. So that's the amount that we're going to need in order to complete this reaction. Let me show you an example of a limiting reactant involved in this sort of equation. So I'm going to scroll down. What if you only had 3 moles of sodium? So if you had only 3 moles of sodium, what is your limiting reactant? Well, that's going to be sodium, because you don't have enough to mix with this to produce this, unless you only had half a mole of iron oxide. So as you can see, it's all about the ratio. So now that we've talked a little bit about what a limiting reactant actually is, let's take a look at an example problem of a limiting reactant. So here what we have is a reaction between butane and oxygen. This is called butane right here, and oxygen and they're combusting to make carbon dioxide and water. So here we're given that we have 430 grams of oxygen and we have 240 grams of butane. Which substance is the limiting reactant? Now I've already started circling this. These coefficients are the numbers that we're going to use in order to determine which one is the limiting reactant. So what we want to find out is what the ratio is between them. So we've got a 2-to-13 ratio, better written as a 1-to-6.5 ratio, because we want to make sure one of them is a 1. That's going to be just a lot easier to understand. So now what we're going to be doing is we're going to be dividing 430 by 240. So, you've got your oxygen on top, your butane on the bottom. We're going to see, whereas, our butane is right here, oxygen is right here, we're going to see how much oxygen we have to each part of butane. So take a moment, we'll calculate that. You should get a 1 to 1.79 ratio. That's what these are divided out. Now, as you can see, 1.79 is smaller than 1.65. This is supposed to be your oxygen. This is supposed to be your butane. Kind of same over here. This is supposed to be your oxygen. This is supposed to be your butane. So since this number is smaller than this one, or this one is larger than this one, I should say, oxygen is the limiting reactant in this problem. So that's the first step. That's how you find out what the limiting reactant is, and feel free to ask questions if you need to. But you're going to be using this to further solve the problem. So we've got a couple of examples, or a couple of questions. The first question is, what is the mass of the product? We want to find out what the mass is of water and what the mass is of carbon dioxide, based on knowing what the limiting reactant is and knowing what the masses are, what the coefficients are. So step 1, determine the limiting reactant. We already did that. It's oxygen. Awesome. Step 2, determine how many grams are in 1 part of oxygen. We have 13 parts oxygen here. So what we're going to do is write down the mass of oxygen that we have right here. So 430 grams of oxygen. We're going to divide that by 13 to get just 1 part of oxygen. Now, you can definitely follow this step later on in the equation too. I like to get it out of the way right away, so I'm just working with 1 part oxygen so far. So however you want to do it, I'm sure it'll work there too. So I've got 33.1 grams in every 1 part of oxygen. I'm going to just write that down here, just so I remember that that's what I was trying to find with this number. 33.1 grams in 1 part of oxygen. All right, step 3, how many moles is that? Now what we want to do is convert that to moles, because remember, grams and moles are different. You can compare the ratios between moles, but you really can't compare the ratios between grams. So here we go, 33.1 grams of oxygen. You'll want to find out what the molar mass of oxygen is. I already found that out just to make things a little easier. So for every 1 mole of oxygen, we have 32 grams here. So gotta label that unit right there. All right, so then as you know from previous problems, or as you should know, you're going to take 33.1 divided by 32. So that's going to get you 1.03 moles of oxygen. This is awesome because 1 is a really easy number to work with. Now we need to find out how many moles of water there's going to be. We're going to be using this coefficient right here, and we're going to be using the number that we just found for 1 part oxygen. So if 1 part oxygen has 1.03 moles in it, then 10 parts of water is going to be 10.3 moles. We're going to just multiply those out. That's, again, why those coefficients are so important. We're going to take 1.03 times 10 equals 10.3 moles of water. And now the next part is actually pretty easy. You're going to convert this to grams, and then you know how much water you should get as a product. So step 3, how many grams is this? So as you probably know, you're going to start with the number that you already have right here. Stick it right down here, 10.3 moles of H2O times, and what is the molar mass of water? You might want to calculate that, or just watch as I write it here. It's 18 grams of H2O for 1 mole. So ideally you would actually write H2O down here, but let's not worry about it too much. So it's going to be 10.3 times 18. That's going to be 186.1 grams of water should be in your product. Now, pause the video for a second and see if you can figure out the same thing for carbon dioxide. Are you able, you would just follow the same exact steps. Grams of product. If you pause the video and you calculated this here number, 362.5 grams, then I think you're on the right track. If not, check with us. There's always that possibility that I've made a mistake too. So definitely check with us. Now you're probably thinking, well, there's an easier way to write this. If you prefer to write this out as like one big long equation, more power to you. That's totally fine too. Whatever works easiest for you, as long as you come to the same answer, then that works too. So here's just another way of writing that out. We're starting with 430 grams of oxygen, and we know that we're going to be trying to find 10 parts of water using 13 parts of oxygen. See how these are opposite? That's how we set that up. And then we're going to write times 1 mole of oxygen is equal to 32 grams. See how, again, these are opposite as well. Times times 18 grams of water over 1 mole. See, this is just a different way of writing this equation out. You can multiply these across and multiply these across, but then divide the numerator by the denominator. If that's easier for you, awesome. I did this on a separate sheet of paper, and this is the number that I got, which is the same exact number as up here, which shows that this way works as well. So feel free, again, to ask any questions if you need to. Um, but this is going to be really helpful for the next video. What you just found here is called the theoretical yield. That's what is going to come out of your equation, ideally based on calculations. So you're going to need that for the next part when you find out percent yield. So, but this is a good skill to have now because you'll need this in your chem quests. All right. Again, feel free to ask any questions if need be.